The universe is vast and strange, brimming with challenges to everything we think we know about reality. From dark flows pulling entire galaxy clusters towards something unseen, to rogue planets drifting through the cosmos with no star to orbit, the universe presents more questions than answers. Even the stars themselves defy expectation. Some survive fiery explosions to become zombie stars, while others are violently ejected across the Milky Way at unimaginable speeds, becoming hypervelocity stars. We're going to journey into the frigid night of starless planets, exploring the possibility of subsurface oceans and geothermal ecosystems, and how life might survive without light. This is a long story, so let's start dreaming. And before we begin, don't forget to like and share. Deep in space, far beyond the confines of our solar system and known galaxies, there is a mysterious phenomenon that has baffled astronomers for years, known as the dark flow. Imagine massive clusters of galaxies, each containing billions of stars, planets, and other celestial bodies, all traversing space together. What is unusual about the dark flow is that these clusters are moving at an inexplicable speed toward a particular direction. According to everything we know about the cosmos, galaxies should be receding uniformly in all directions due to the expansion of the universe. This means that as space itself stretches, galaxies should drift apart from each other. But the dark flow suggests something different. These galaxy clusters are moving against the expected flow, as if being tugged by something beyond our current ability to observe and understand. The movement is fast and eerily coherent, as if they are being pulled by an unseen force, a gravitational influence originating from a region of space that is simply invisible to us. What could be there? One of the most fascinating ideas is that these massive clusters are being pulled towards the edge of the observable universe. The observable universe is the part we can see with our telescopes, limited by the speed of light. Beyond this boundary, perhaps there is something incredibly large and powerful that is dragging entire galaxies towards it, but which we cannot directly observe. We can only speculate about what lies hidden beyond the cosmic horizon. Some scientists hypothesize that the pull might be a massive structure, perhaps a huge concentration of extremely dense matter that exerts a powerful gravitational influence on a cosmic scale. It's like a behemoth lurking just out of sight, yet capable of tugging objects millions of light years away. Others suggest the dark flow could be a sign of something much stranger, perhaps a connection to another universe or a region of spacetime operating differently from our own. This leads to the mind-bending possibility: what if there is an entire other universe just beyond our observable edge? Could the force pulling these galaxies be a bridge connecting different domains of spacetime? If so, it suggests our universe is just one bubble in a larger cosmic ocean, one piece of a multiverse. The idea that these galaxies are being dragged toward a hidden domain, an unobservable existence, opens up questions we are barely equipped to answer. Are they heading toward a region where the laws of physics are different from ours? The dark flow may be evidence of a deeper, more profound cosmic structure, and we are only seeing the tip of the iceberg. Perhaps there are forces or objects that don't behave the way we predict, or perhaps these galaxies are moving towards something entirely outside the universe as we know it, something we cannot even conceive of with our current understanding. Who is pulling these galaxies, and why? If you imagine the universe as a vast tapestry with stars and galaxies woven into it, it's as if an invisible hand is grabbing a thread and pulling a section of the cosmos toward an unknown destination. The scale of this movement is staggering. These galaxy clusters are among the largest structures in the universe, and the way they are being moved suggests an existence or a force much larger and more powerful than anything we are currently aware of. Could it be an entirely different region of spacetime where the physics we are familiar with either breaks down or manifests in different ways? The fact that these galaxies are being drawn to an unknown, unseen target is both mesmerizing and unsettling. It raises a host of fundamental questions about the nature of the cosmos. Does space have an edge? Or are these galaxies traveling along a path towards something that lies beyond our comprehension of existence itself? Some theories suggest the dark flow might be an indication of a hidden structure or a leftover mass from the very earliest moments of the universe, formed in the brief instant after the Big Bang. If this is true, the cause of the dark flow has been influencing the cosmos for nearly 14 billion years, operating since the universe's infancy. But even this doesn't explain where these galaxies are ultimately going. It only suggests they have been moving in this direction for an extremely long time. What if the dark flow points to a more profound truth? What if our understanding of cosmic expansion is incomplete, and there are forces at play we have yet to discover? If so, our entire model of how the universe works, its structure, its growth, and its future, may need to be revised. The possibility that the dark flow points to regions or forces in the cosmos that are beyond our comprehension excites the imagination and forces us to question the universe we thought we knew. If these galaxies truly are being pulled towards something outside the observable universe, we have to confront the tantalizing possibility that our cosmos is merely a small part of a far grander, stranger reality. Late in 2017, something extraordinary happened. For the first time in recorded human history, an interstellar visitor from outside our solar system passed through, leaving more questions than answers. It was named Oumuamua, and its elongated, cigar-like shape, abnormal speed, and trajectory suggested one thing: this was no ordinary space rock. Oumuamua came from beyond our system, and when it was first detected, astronomers were baffled. Initially, they thought it might be a comet, but it didn't exhibit the typical outgassing of vapor and dust when it neared the Sun. Then it was considered an asteroid, but its shape and behavior didn't align with any known asteroid. Oumuamua was long and thin, like a stretched cigar, and was tumbling end over end as it flew. No naturally formed object of this shape or movement had ever been observed before. As it continued on its path, it was discovered that it was moving faster than predicted. It was not following the path usually taken by objects in the solar system. Instead, Oumuamua seemed to be accelerating as it moved away from the Sun, defying the gravitational pull that should have slowed it down. This unexpected acceleration added another layer of mystery to an already bizarre object. One of its most striking features was its origin. All signs pointed to it not being from within our solar system but being an interstellar visitor. It crossed unimaginable distances to get here from another star system. The nearest star system, Alpha Centauri, is more than 4 light-years away. Such a distance is almost incomprehensible. Whatever Oumuamua's point of origin, it may have drifted through the cold, empty expanse of interstellar space for millions, or even billions, of years before stumbling into our solar system. But where did it come from, and what exactly was it? These questions spawned a variety of theories. Some scientists suggested it might be a fragment of a planet or asteroid that was torn apart after a violent collision in another star system. Over time, the fragments were ejected from their home system and hurtled through interstellar space, eventually reaching us. If so, Oumuamua could be a piece of a distant world, a cosmic shard from a place we may never know. Another possibility is that it was a comet that had lost most of its volatile material during its long journey. If this is the case, it may have started out like a typical comet, but after millions of years of interstellar wandering, it lacked the material to form a bright tail when approaching the Sun. This could explain why it didn't look like a typical comet but still exhibited some anomalous acceleration. However, its strange shape, rapid rotation, and anomalous acceleration led some scientists to propose a more radical possibility: could it be an artificial object? Was Oumuamua's elongated shape and strange behavior potentially an alien probe or spacecraft? This idea, though speculative, certainly captured the imagination of many, especially because the acceleration is difficult to explain through known natural processes. Someone hypothesized that if it were an alien probe, it might use propulsion methods we don't yet understand, and its long, thin shape could be specifically suited to minimizing drag in space. Others suggested it might be a light sail, a structure that is ultra-thin and lightweight, propelled by stellar radiation. This isn't pure science fiction. Humanity has developed light sails for small spacecraft, and a more advanced civilization could potentially build them larger and more complex. Of course, viewing Oumuamua as an extraterrestrial vessel remains highly controversial. Most scientists believe a natural explanation is more likely, pointing to the lack of direct evidence for an artificial structure. But the fact remains, it was unprecedented, and its strange characteristics continue to fuel debate. Oumuamua's passage through our solar system was brief. It zipped past the Sun and headed out, giving us only a limited observation window. As it moved farther away, it became increasingly difficult to track until it eventually vanished from sight entirely. Since then, scientists have continued to analyze the data collected during its short visit, trying to unravel the mystery. Its most compelling significance is that it reminds us that the solar system is not an isolated bubble in space. We are part of a far grander, interconnected cosmos, full of objects, forces, and phenomena we are only beginning to understand. The fact that Oumuamua came from another star system shows that interstellar travel is possible. This suggests that other interstellar visitors like Oumuamua may have passed through our solar system unnoticed before and will surely come again. It also makes us wonder about the origin of these objects. If Oumuamua is just one of many interstellar travelers, what else is out there? Are they carrying clues about the formation of distant worlds, or perhaps even relics of ancient civilizations? As we continue to explore the vastness of the cosmos, we find that the universe is far from a perfectly ordered, balanced place. At first glance, it might seem that galaxies, stars, and planets are spread evenly throughout, but the reality is more complex. The actual universe is tilted and lopsided, with an uneven distribution of matter, and this raises scientific questions and debates. For a long time, we believed that on a large enough scale, the universe should be approximately uniform. This idea stemmed from the assumption that the Big Bang would create a cosmos where matter and energy were relatively evenly distributed. But upon closer inspection, this isn't the case. Some regions are richer in matter, while others are much sparser. Why did the universe form in such an unbalanced way? One explanation suggests that something unusual happened during the universe's earliest moments. Shortly after the Big Bang, the universe underwent a brief but dramatic burst of rapid expansion. During this time, the tiny fluctuations in matter density were amplified, leading to the uneven distribution we see today. If the initial fluctuations were very small, over billions of years they would have been magnified, creating areas where matter clustered together in regions that were largely empty. However, this theory only explains part of the non-uniformity and struggles to fully account for the scale of imbalance we observe. It's as if other factors are at play. Some scientists believe that dark matter, the invisible component that makes up the bulk of the universe's matter, plays a role. Dark matter doesn't interact with light, so we can't see it, but its gravitational effects are visible, tugging galaxies together and shaping cosmic structure. Perhaps dark matter contributed to the universe's asymmetry in ways we don't yet understand. Others propose that this non-uniformity might stem from forces or events we haven't yet discovered, perhaps a deeper law of the universe that inherently favors asymmetry. If so, it challenges our ideas about the nature of the cosmos. We are used to thinking of the universe as a place where order and symmetry prevail, but deeper investigation reveals that chaos, unpredictability, and non-uniformity are equally fundamental to its character. This also raises more philosophical questions. Does the universe's imbalance suggest that asymmetry is a fundamental property of existence? If the universe itself is uneven, does that mean that imbalance and chaos are ingrained at the core, from the smallest particles to the largest galaxies? On Earth, we often see symmetry as a mark of beauty and perfection. We favor balance and patterns, whether natural or man-made. But when we look at the cosmos, this largest structure follows different rules. It is messy, uneven, and irregular. Yet, amidst the universe's non-uniformity, order still emerges. Galaxies form, stars are born, and planets appear. It seems that this very asymmetry enabled the universe to evolve and generate the complexity we see today. If the universe were perfectly uniform, perhaps no structure would ever have formed. No galaxies, no stars, no planets, just a featureless expanse of smooth space. Instead, the universe's non-uniformity prompted matter to clump together, forming galaxies and ultimately leading to life. Thus, the universe's lopsidedness might not be a quirk, but a necessary condition for its existence. Even so, we continue to ask, why is it this way? Does the uneven distribution of matter point to forces we haven't yet grasped? Some even suggest that this tilt might be a clue to the universe's origin. If the universe started with some imbalance built into it from the very beginning, it might explain why it evolved the way it has. But if so, where did the initial non-uniformity come from? Did the universe have a chaotic beginning, dominated by randomness and asymmetry? Or is there a deeper reason, some unknown force that made the universe this way? Another line of thought is that the laws of physics inherently favor the breaking of symmetry in certain processes. Symmetry is naturally flawed, leading to the uneven structures we observe today. This is true on small scales as well. In the quantum world, particles often behave asymmetrically and unpredictably, and perhaps this is reflected on the largest scales too. The universe's lopsidedness may be a reflection of a deeper, fundamental principle. Even more audacious ideas connect the non-uniformity to other universes. If our universe is just one of many, could the asymmetries we observe be influenced by these other universes, or the pull or gravitational effects from beyond our cosmos also be shaping the lopsided distribution of matter? This raises even more questions about the nature of reality. Is our universe isolated, or is it connected to something much larger? Whatever the cause, the fact remains, the universe is uneven, and this unevenness plays a key role in shaping everything. The cosmos is not a perfectly ordered, symmetrical place, it thrives and grows in irregularity and imperfection. Thus, the unbalanced universe challenges our understanding of order and chaos. Even the most grand structures may be shaped by forces that favor asymmetry. In the vast reaches of the cosmos, time does not behave as we perceive it. The uniform tick-tock we experience is profoundly influenced by the forces and velocities around us. This is time dilation. Time can slow down or speed up depending on where you are and how fast you are moving. It challenges our understanding of what time is and raises questions about how life might perceive the cosmos in different corners of the universe. Time dilation occurs in two extremes: when an object is moving close to the speed of light, or when it is near an extremely strong gravitational field. In both scenarios, time slows down dramatically. For travelers moving near the speed of light or for those living near a black hole, seconds would stretch, minutes would crawl, and hours could feel like an eternity. This is not science fiction, it is a measurable effect confirmed by science on Earth. For example, GPS satellites, moving at high speeds above Earth, have clocks that run slightly faster than those on the ground. If this wasn't corrected, the system would quickly become inaccurate. But the effect in orbit is minuscule compared to what happens at the edge of a black hole. A black hole's gravity is so intense that it warps both space and time. Imagine standing on the surface of a planet orbiting close to a black hole. The black hole is huge, and its gravity stretches and warps your time. For you, time would feel nearly normal, but if you looked out at the distant universe, their experience of time would be radically different. Only a few hours might pass for you near the black hole, yet days, months, or even years could pass for a distant observer. The closer you get to the black hole, the more profound this effect becomes. If you were suspended just outside the event horizon, time would slow down almost to a stop. In your view, the outer universe would appear to speed up. Stars would seem to age and die faster, galaxies would collide and merge, and the entire universe would flash by in a blur, while you would barely age at all. It is difficult to imagine how life living in such an extreme gravitational environment would perceive the cosmos differently. If we were to encounter them, they might see us in fast forward, while we might perceive them as almost frozen. Could we even communicate, or would the difference in the perception of time be too great to bridge? The fact that time changes based on location and speed shakes our very notion of reality. On Earth, we treat time as a constant that flows steadily forward, but the universe does not abide by this rule. Time is not a fixed construct but a quantity that can be bent and altered by different forces, and it is intrinsically linked to space, forming the dynamic fabric of space-time. The very reality for life in different regions of the universe could differ due to the variance in the flow of time. Those near black holes would see the external cosmos speeding by to an incomprehensible degree, while we on Earth would see them moving at a frustratingly slow pace. Is it possible there are civilizations residing near a black hole, living at a fraction of our speed of time, completely unaware that eons have passed on our side? Time dilation also raises questions about an extraterrestrial encounter. What would a meeting be like if our times were out of sync? Could we even communicate effectively? It also impacts our understanding of interstellar travel. If we travel close to the speed of light, our own time will slow down relative to Earth's time. Thus, an interstellar journey that appears to take centuries from Earth's perspective might only take a few years for the traveler. This makes a cross-star journey more conceivable from the traveler's perspective, but for those left behind, generations may have passed. So, we are forced to ask, is time truly the stable, unchanging quantity we assume it to be? Or is it a phenomenon that flows and changes based on location and velocity in the cosmos? If time is not constant, what then is the nature of reality? Could it be that our perception of time is just one reality among many, entirely foreign to life elsewhere? In a universe where time varies with location and speed, reality becomes a relative concept. For us, time seems linear, with every second being equally long, but for those moving near the speed of light or those dwelling on the edge of a black hole, the experience of time is completely different. Does this mean that there are multiple versions of reality throughout the cosmos, governed by different rates of time flow? These questions have no simple answers, but they force us to think about the universe in new ways. Time, it seems, is not the straightforward, constant thing we once thought it was, but a more complex entity that changes depending on where you are and how you move. And reality, and our place within it, must be re-evaluated because of this. Among the myriad stars in the Milky Way, there are countless planets. Many orbit a star, much like Earth orbits the Sun. But not all planets have a home. Some drift coldly through the cosmos with no star to call their own. These are the rogue planets. Unlike the familiar planets bound by a star's gravity, rogue planets float freely through space, isolated and unbound. Some estimates suggest that there may be more rogue planets in the Milky Way than there are stars. How they came to be is still debated. One idea is that they were once part of a busy planetary system but were ejected during the chaotic gravitational scramble of early formation. During the phase when planets are forming and jostling for position, some can be flung into interstellar space by the complex gravitational interactions of other planets and their host star, becoming exiles. Another possibility is that they formed alone from the start, never part of a star system. In the massive clouds of gas and dust within a galaxy, matter could directly collapse to form a planet, but one that had no star to orbit from the beginning. What would the environment of such a world be like? Far from the light and warmth of a star, surface temperatures would plunge to extremely low levels, resulting in a world covered in ice. Yet, they might not be completely lifeless. Some scientists speculate that if a planet possesses a thick atmosphere or an internal heat source, it could still maintain some warmth beneath the surface. On Earth, life can survive in the most extreme places, the crushing depths of the ocean, the frigid cold of the poles. Is it possible that life could survive beneath the surface of a rogue planet? One scenario suggests that a thick atmosphere to retain heat, combined with internal heat from the planet's core, could sustain liquid water beneath a shell of ice. This brings to mind Europa, Jupiter's moon, which may have an ocean beneath its icy crust. Similar subsurface oceans could exist on rogue planets, but fueled by geothermal heat rather than sunlight. In such an environment, any life would likely be completely different from surface life on Earth. With no sunlight for photosynthesis, life would have to rely on other energy sources, such as geothermal vents and minerals, much like the ecosystems found near deep-sea thermal vents on our own planet. Another radical thought: could there be forms of life that have adapted to the harshness of space? Earth's extremophiles can survive in unimaginable conditions: high temperatures, extreme cold, intense radiation, and crushing pressure. If Earth life can do this, is it possible that life on rogue planets could have adapted to even more severe environments? Observationally, rogue planets are extremely difficult to detect. Without a star to illuminate them, they are invisible to most instruments. We can only catch glimpses of their presence through indirect methods like gravitational microlensing. This occurs when the rogue planet's gravity briefly bends and magnifies the light from a background star, allowing us a fleeting glimpse of its existence. But if their numbers truly exceed the stars, what we've seen might be only the tip of the iceberg. They could also provide clues to understanding the history of our solar system. If planets can be ejected, it is possible that the solar system once had more planets, some of which were exiled into the cold void during the long gravitational interplay, becoming rogues. The existence of rogue planets also subverts our ideas about the relationship between planets and stars. Planets don't always need to be subservient to a star; some are destined to wander alone, and this highlights the dynamic and often violent nature of the cosmos, where even objects as massive as planets can be flung out by gravity. In contemplating the vastness and strangeness of the universe, there is a concept known for its sheer bizarreness: the Boltzmann brain. These theoretical self-aware entities are not formed through biological processes or evolution but are proposed to arise from the random fluctuation of particles in space. The idea is that if time is long enough and the universe is large enough, random fluctuations could, purely by chance, spontaneously assemble a fully conscious mind from chaos. It would be self-aware but utterly alone in the void. The concept originates from Austrian physicist Ludwig Boltzmann, who explored entropy and randomness in the universe in the late 19th century. He proposed that over vast timescales, random fluctuations could occasionally create order out of chaos. Modern thinkers extended this to consciousness. Could random processes also spontaneously create a transient mind? A Boltzmann brain is imagined to arise in the empty regions of the universe, where particles are aimlessly drifting, colliding, and separating. Most of the time, they would only form random, non-ordered patterns. But in an incredibly rare chance event, they might spontaneously arrange themselves into a structure complex enough to think and perceive. A Boltzmann brain is not formed slowly through evolution but is born instantaneously, constructed directly by a random alignment of particles. It has no history, no body, and no connection to the surrounding universe. It is simply a thinking, self-aware mind, floating alone in cold, dark space. This challenges our understanding of consciousness and existence. Humans have long assumed that consciousness arises from complex biological systems, evolved brains, bodies, and neural networks. But the Boltzmann brain suggests that, theoretically, consciousness could appear spontaneously purely by chance. This leads to a troubling question: What does it mean for the nature of consciousness if a mind can simply pop into existence from nothing? Even more unsettling is the idea that, in the scenario of an infinite universe, Boltzmann brains might be far more common than biological minds. Because in infinity, any possible event will happen an infinite number of times. Even though the formation of a Boltzmann brain at any given moment is extremely unlikely, over infinite time and space, these rare events would still be numerous, perhaps even outnumbering biological minds, which require specific conditions and a long evolutionary process. This leads to a chilling question: could we ourselves be a Boltzmann brain without knowing it? For a Boltzmann brain, there is no way to distinguish if the reality it perceives arose from natural evolution or from a random, instantaneous construct. It might have seemingly real memories, thoughts, and experiences, but they would be nothing more than the product of chance. In a sense, it lives in a delusion, unaware that it was just created and that its so-called memories have no history. This hypothesis forces us to confront difficult questions about the nature of reality. If a mind can be born from random fluctuations, how can we be sure of the stability and consistency of our own reality? Could our memories and experiences also be merely the products of chance? Of course, most scientists consider the Boltzmann brain to be a mere thought experiment, with no evidence that we are one. Its significance lies in forcing us to consider the limits of our understanding of consciousness and the universe. It also touches on deeper philosophical questions, existence and solitude. If a Boltzmann brain were to form, it would be utterly isolated, unlike life embedded in an ecosystem, a society, and a civilization. It has no connection to the world, a disembodied mind, a consciousness without community, floating in space, unable to interact with or understand its surroundings. What does this isolated existence mean? Does consciousness require interaction with the world to be valid, or can it exist in isolation? If a Boltzmann brain can think and perceive without external stimuli and without a physical form that produced it, does that suggest that consciousness is more fundamental than the material world, or is it inextricably linked to the biological system that gave rise to it? For some, the Boltzmann brain symbolizes a kind of cosmic solitude. The universe is vast, cold, and mostly empty, and a mind that pops into existence by chance is destined to drift alone. It is both fascinating and deeply unsettling. It hints at the fragility and subtlety of the balance that allows our minds to exist and function. At the same time, it is a reminder that in the randomness and probability of the cosmos, the most improbable events are not impossible. If a mind can arise from chance, what other forms of existence might be out there in an unpredictable universe? Across the immense expanse of the cosmos, stars generally shine in predictable ways, with subtle variations in brightness often due to understandable phenomena like sunspots or passing planets. But occasionally, a star defies the norm. Tabby's star KIC 8462852 is almost unprecedented, baffling scientists with its extreme and irregular variations in brightness and fueling a huge array of speculation. The story began in 2015 when a team led by Tabitha Boyajian discovered the anomaly while analyzing data from the Kepler Space Telescope. Kepler searches for exoplanets by monitoring tiny, repeatable dips in starlight. But the dips in Tabby's star were not the regular, repeating pattern indicative of a planet. Instead, it would suddenly and dramatically dim, sometimes by as much as 20%, before slowly recovering. These fluctuations were irregular, sometimes fast, sometimes slow, and often without a discernible pattern. Such extreme and unpredictable dimming had never been seen before, and no natural processes struggled to explain why this star would dim so severely. For years, the theories ranged from the mundane to the truly extraordinary. Early ideas focused on natural phenomena. Perhaps a vast cloud of dust or a swarm of comets was passing in front of the star, blocking its light. But as more data accumulated, these explanations proved increasingly inadequate. For instance, the comet swarm hypothesis would require an astonishing amount of material to cause such dramatic dimming, far exceeding the scale we see in our own solar system. Interstellar dust was also considered. A cloud of fine dust could block or scatter starlight. However, different dust compositions exhibit characteristic dimming at different wavelengths, and the observations did not show the expected wavelength dependence. As natural explanations struggled, a more outlandish possibility emerged. Could an alien megastructure be blocking Tabby's star's light? A highly advanced civilization, far beyond our own, might be building colossal structures around the star, perhaps to harvest energy. If such a structure were still under construction or incomplete, it could cause the irregular dimming. This scenario, while highly speculative, was seriously discussed. However, most scientists remain cautious. Despite the compelling imagination, there is no direct evidence supporting an alien megastructure. Meanwhile, more data has brought new clues. In addition to the short, sharp dimming events, Tabby's star also seems to be undergoing a long-term, slow dimming of its average brightness. This has led some researchers to propose that a massive cloud of dust or debris is floating around the star, possibly originating from a planet or moon that was tidally disrupted. If a large celestial body was shredded by the star's gravity, it could create a cloud of dust and debris that periodically passes in front of the star. The long-term dimming could then be explained as this dust cloud slowly dissipates. But even this scenario has challenges. The debris cloud needed to cause such a degree of dimming would have to be incredibly massive and volatile. And how does this cloud remain stable for such a long time? Each new observation seems to bring as many new questions as answers. Tabby's star is so captivating precisely because it resists categorization. Its dimming doesn't fit any known pattern of stellar behavior, making it one of the most enduring astronomical mysteries of our time. It has also sparked a broader discussion that what we know might be far from complete. Perhaps the star truly has a debris cloud of planetary remnants, or perhaps it reveals a phenomenon we haven't even imagined. And the alien megastructure, while a tempting speculation, must be treated with extreme caution. Observations are ongoing across multiple wavelengths, hoping to zero in on the truth. Whatever the conclusion, Tabby's star has captivated the global imagination, showing that even in a universe so vast, there are still deep mysteries that can shock us. The universe is often thought of as a massive background of general uniformity, yet within it hide anomalies that defy easy explanation. The Eridanus supervoid, or the CMB cold spot, is one of them. It corresponds to a giant cold patch on the cosmic microwave background (CMB) radiation, spanning nearly 1 billion light-years, located in the direction of the Eridanus constellation. It has caused intense scientific debate. Is it merely an unusually large void, an area nearly devoid of galaxies and matter, or is it something more profound, perhaps the imprint of a collision between our universe and another, offering a glimpse into the multiverse. The CMB is a snapshot of the universe about 380,000 years after the Big Bang, and it is extremely uniform, with only tiny temperature differences reflecting the early density perturbations of matter. These perturbations later led to the formation of galaxies and clusters. But in the region of the Eridanus supervoid, the temperature is significantly colder than the surrounding area. At first, a natural explanation was the most logical. Perhaps this is just an exceptionally large void. Voids are not uncommon in the universe. They are vast expanses of space, hundreds of millions of light years across, where matter is sparse and there are almost no galaxies. Light passing through a void loses energy, making it appear colder when it reaches us. The problem is that the size and coldness of this patch are far greater than what can be explained by just a giant void. This led some to suggest that it may not be a simple void, or that something more extraordinary is happening within the void itself. More imaginative theories suggested that this might be the bruise of a past collision between our universe and another. This connects to the idea of the multiverse. In some versions of inflationary theory, the rapid expansion of the early universe could have produced not just one universe but many, each with its own set of physical constants and laws. These bubble universes might exist parallel to each other but could occasionally interact. If a universe-to-universe collision actually happened, the resulting energy disturbance could have left a lasting mark on the CMB, such as an unusually cold spot like this one. If true, it would be a staggering discovery, the first time we might have seen evidence of another universe. Of course, the multiverse collision remains highly speculative. Another, more conservative possibility is that the cold spot is simply an extreme statistical outlier. In a cosmos this immense, such an anomaly doesn't necessarily require a bizarre explanation. It may simply be an extreme but natural void. The debate continues, and new observations and simulations may reveal whether this is a unique anomaly or a piece of a larger structure hidden deep within the cosmos. Either way, this cold, empty region forces us to consider whether our universe is just one part of a larger reality. The evolution of stars appears predictable: birth, burning, depletion, death, leaving behind remnants that tell the tale of their glorious past. Many stars end their lives as white dwarfs, having exhausted their fuel and collapsed into a dense, compact remnant that can no longer sustain fusion. But even in death, some stars defy expectation. Some survive a thermonuclear explosion, seemingly refusing to die. These are the zombie stars. They typically occur in binary systems, where one star has reached the end of its life and become a white dwarf, and the other is still burning. The white dwarf's strong gravity siphons hydrogen and helium from the outer layers of its companion. As the accretion continues, the white dwarf's mass approaches the Chandrasekhar limit, the boundary where internal pressure is just enough to reignite nuclear fusion. This isn't a slow renition but a thermonuclear runaway explosion, a Type Ia supernova. Type Ia supernovae are extremely luminous, briefly outshining entire galaxies, and they are critical standard candles for measuring cosmic distances. The traditional view holds that the white dwarf is completely obliterated in this explosion. But in rare instances, something extraordinary happens: the white dwarf survives. Instead of being vaporized, it remains a remnant, a zombie refusing to vanish. This challenges our understanding of stellar physics. In the standard Type Ia scenario, the star is shredded by the explosion. But in the case of a zombie star, it appears the outer layers ignited the explosion, leaving the core relatively intact. The outer shell is blown away, and the dense core survives, becoming a faint, hot remnant. What's more, the survivor might even continue to accrete material, possibly undergoing multiple, smaller reignition bursts. One famous example is the remnant of SN2012Z, where a white dwarf was still visible after a Type IX supernova, a weaker variant of the Type Ia explosion. This suggests that some white dwarfs undergo less violent explosions, allowing them to survive and continue accreting from their companion for a long time before potentially undergoing another, final explosion. The existence of zombie stars forces us to re-examine the neat pathways of stellar life and death. It also hints that Type Ia supernovae may not be perfectly uniform, which could have implications for how we use them to measure the expansion of the universe and understand dark energy. The exploration of the cosmos is rife with deep mysteries, and one of the largest is dark matter. We cannot see it, touch it, or directly detect it, yet it accounts for about 85% of all matter in the universe. In typical galaxies, stars, gas, and dust shine, while dark matter provides the unseen scaffolding. But Dragonfly 44 pushes the boundary of this concept to the extreme. Discovered in 2016, this galaxy is almost entirely composed of dark matter, with so few stars that it is virtually invisible in visible light, earning it the moniker of a dark matter galaxy. Dragonfly 44 is located about 330 million light-years away in the Coma cluster. It was first detected not by its faint light, but by the gravitational effect it had on its environment. Measurements showed that its total mass far exceeded what could be explained by its visible stars. Its overall mass is comparable to that of the Milky Way, yet it contains less than 1% of the Milky Way's stars. Scientists measured the velocity of its few stars and found they were moving much faster than the visible mass could possibly bind, indicating a huge, unseen mass holding the structure together. Dragonfly 44 raises a key question: how did it form? In most galaxies, stars gradually form as gas clouds collapse and ignite, but in Dragonfly 44, this process seems to have been interrupted early on. Perhaps it was once a normal galaxy, but an early interaction or collision choked off star formation. It could also be a relic galaxy, an immigrant from the early universe when dark matter dominance was stronger. If so, studying it could help us understand the behavior of dark matter on large scales and the formation of early galaxies. Since Dragonfly 44, more ultra-diffuse galaxies (UDGs) have been discovered. They are vast in area but sparse in starlight, dominated by dark matter, and are often described as ghostly and tenuous. As technology improves, we may find many more of these almost pure dark matter galaxies, bringing us closer to understanding the true nature of dark matter. In the stillness of space, most stars follow their orbits elegantly, but a very few are rebels, the hypervelocity stars. They are not bound by gentle gravity but are ejected at speeds of thousands of kilometers per second, fast enough to escape the gravity of their home galaxy and become intergalactic vagabonds. This challenges our understanding of cosmic forces, especially the extreme environment at the galactic center. The dominant mechanism involves the supermassive black hole at the heart of a galaxy. When a tight binary star system gets too close, the intense gravity tears them apart. One star is captured by the black hole, and the other is violently flung out of the galaxy with escape velocity. This binary disruption mechanism is the most powerful explanation we currently have. The ejected stars become true cosmic wanderers, drifting through the intergalactic void for billions of years. Some may not escape the large gravitational pull of their galaxy cluster and might eventually be recaptured by a neighboring galaxy. Other possibilities exist. Complex gravitational interactions with massive star clusters or smaller black holes can also accelerate a star. A famous example is US 708, an extremely fast hot subdwarf star, clocked at over 1,200 kilometers per second. It may have been part of a binary system with a companion that exploded as a supernova, and that explosion gave it a kick, launching it out of the Milky Way. Hypervelocity stars also serve as probes, helping us map the gravitational distribution inside and outside galaxies, particularly the unseen hand of dark matter. Crossing unimaginable distances in space-time, the light that reaches Earth doesn't always travel in a straight line. When it encounters a massive object along the way, it gets bent and distorted. This is gravitational lensing, and it creates strange illusions, allowing us to see into the universe's most distant corners. One such phenomenon is the double quasar. From Earth, it appears as two bright points, but it is actually two images of the same quasar, separated by the gravitational lens of a foreground galaxy. Quasars are some of the brightest objects in the universe, intense light sources powered by supermassive black holes devouring matter in distant galactic centers. Because they are so far away, we see them as they were billions of years ago. Gravitational lensing allows us to view the same target from multiple angles and simultaneously study the foreground lensing galaxy. In the 1970s, the light from a quasar was first discovered to be split into two close points. Initially, it was thought to be two nearby quasars, but detailed comparison showed their spectra were identical, confirming they were two images of the same object. Because the two light paths take slightly different routes, they arrive at Earth at different times, creating a time delay that can range from days to years. This allows us to see the same event twice, effectively observing it from two different points in time. By analyzing the distortion and delay of these images, scientists can deduce the mass and structure of the foreground galaxy, even mapping the distribution of its dark matter. In the rare case of a perfect alignment, the quasar's light is stretched into a closed circle, an Einstein ring. These provide even more detailed information about the mass distribution but are much rarer. Q0957 plus 561, one of the famous double quasars, had its time delay observations used to help measure the expansion rate of the universe and map the dark matter distribution in the lensing galaxy cluster. In the universe, which often resembles islands scattered in the sea, there is one enormous empty region, the Boötes void. It spans about 330 million light-years and contains remarkably few galaxies, baffling and fascinating scientists. Voids are generally thought to arise from the earliest perturbations, where matter was slightly underdense. High-density regions coalesced into galaxies and clusters, while low-density regions evolved into voids. But the Boötes void is unusual in both its size and emptiness, as if it was deliberately cleared out. One hypothesis is that it is a natural result of the long-term evolution of the universe and the migration of galaxies. However, its sheer size still makes some suspect other causes, such as anomalous behavior of dark matter in the region or even stranger physics. It also reminds us that while we observe the visible galaxies, stars, and nebulae, the universe's primary color is emptiness. Voids are not nothing, they are part of the larger cosmic web that, along with matter, shapes the structure of the cosmos. Black holes are famous for swallowing everything with their immense gravity, but the same set of equations from Einstein's general relativity also permits a mirror image solution, the white hole. If a black hole's event horizon is a point of no return, a white hole's is a region that cannot be entered, only spitting out matter and energy. However, white holes remain purely theoretical and have not been observed. Whether a mechanism exists to form a white hole remains unknown. Some hypotheses link white holes to the Big Bang, viewing the universe's initial eruption as a white hole-like event. Others are more daring. Perhaps white holes and black holes are connected by wormholes. Matter falling into a black hole could travel through a wormhole and be ejected from a white hole at the other end, potentially even into another universe. But wormholes are considered highly unstable, requiring exotic matter with negative energy density to keep them open. Attempts have also been made to link the immense energy of gamma-ray bursts to white hole eruptions, but this remains speculative. The mystery of the white hole pushes us to question the limits of the arrow of time, the fate of information, and the structure of space-time. For a long time, we assumed the core of a black hole was a singularity where the laws of physics break down. Recently, a new idea has emerged. When a black hole shrinks to the Planck scale, quantum gravity effects dominate, and a quantum bounce might occur, forming a so-called Planck star and avoiding the singularity. This attempts to merge general relativity with quantum mechanics. At extremely small scales, gravity behaves differently than in classical terms. The collapse creates a repulsive pressure at the quantum level, preventing further collapse and turning it into a bounce that releases energy over extremely long timescales. This is different from the slow evaporation of Hawking radiation and is hypothesized to be a concentrated energy release event at a certain moment. If true, black holes might not be a terminus but the ultimate rebound of matter conversion. The energy released might even forge new cosmic structures. This could also offer a way out for the information paradox. By avoiding the singularity, information would not be absolutely destroyed but released in some form during the bounce. The challenge is that this happens inside the event horizon, making direct observation difficult, though certain radiation or sudden perturbations to surrounding matter could be indirect clues. The universe is expanding, a revolutionary discovery of the 20th century. Even more astonishing were observations in the late 1990s showing that this expansion is accelerating, driven by dark energy. If dark energy strengthens over time, the universe's fate could lead to one of the most terrifying scenarios, the Big Rip. According to this blueprint, in the far future, the universe would accelerate to the point where even the gravitational pull of galaxy clusters cannot hold them together. Then galaxies themselves would be ripped apart. Next, planets would be torn from their stars, and moons from their planets. Eventually, the stars themselves would fail to hold together, exploding into gas and dust. Even more dramatically, the bonds at the atomic level would be stretched apart. Molecules would disintegrate, and eventually, even protons and neutrons would be torn apart by the expansion of space itself. The universe would be left as a thin, cold soup of subatomic particles, becoming ever emptier in its endless expansion. Of course, the Big Rip is just one of several potential endings. Others include the Big Freeze, where the universe continues to expand, stars burn out, and energy is uniformly dispersed, leading to a long night where nothing ever happens. There's also the Big Crunch, where expansion reverses, and the universe collapses back in on itself, potentially leading to another Big Bang. Whichever it may be, the ultimate fate of the universe is as much a philosophical question as a scientific one. It forces us to confront the impermanence of all things and the scale of time and distance far exceeding human intuition. Beyond the black holes residing in galactic centers or stellar remnants, there is a more elusive class, rogue black holes. They are unbound by any galaxy or star, drifting alone in the vast emptiness of interstellar or intergalactic space. Formation mechanisms may include a three-body interaction where a binary black hole system is disrupted by a third massive body, ejecting one of the black holes from the galaxy. Or, a black hole merger could generate a powerful recoil, kicking the newly formed black hole out of its host galaxy. They could also be primordial black holes, formed directly from high-density fluctuations in the early universe, never captured by a system. They are silent and dark, nearly impossible to see directly, but they bend background light or perturb the motion of nearby sparse gas and stars, providing potential clues. If rogue black holes are numerous, they might play a previously unrecognized role in the mass budget and structural evolution of the universe. At the center of the Milky Way sits a supermassive black hole with a mass of about 4 million suns, Sagittarius A SGRA. Unlike the active counterparts in other galaxies that spew out blinding radiation and jets, SGRA is remarkably quiet, emitting only faint X-rays and radio waves with no significant jets. This raises the question, is it simply eating very little? A low accretion rate could explain the quietness, but why is the rate so low? Was it once more active? The galactic center shows signs of strong past star formation and energetic activity, suggesting SGRA* may have gone through peak periods, followed by a lull. The dense concentration of stars and gas clouds around it, along with complex magnetic fields and physical conditions, may influence the efficiency and manner of its current feeding. Feedback mechanisms may also be self-regulating. Past eruptions could have blown away material and energy, reducing subsequent accretion. To solve this mystery, astronomers combine observations across multiple wavelengths, radio, X-ray, and others, and use numerical simulations to explore different scenarios. The Event Horizon Telescope is also working to resolve the details of SGRA*'s Event Horizon neighborhood. This is not just about the character of one black hole, it will inform our overall understanding of galaxy formation and black hole growth. That concludes today's sharing of knowledge. I wish you all a beautiful dream and a wonderful day. We will see you next time.